Good. So let's see where we stopped last time, right? So I was doing all sorts of calculations based on the first part of Newton's first law, okay? So there are two parts. Let's write that down here. There are two parts for Newton's first law, okay? One, the first part is for objects at rest. And two, the second part is for objects moving, very important, with constant velocity, okay? Constant velocity, not acceleration. And you must memorize those laws. That's how important they are. They're so important that you have to memorize them. Have to memorize them for the rest of your lives, okay? Remember, it took a huge amount of work for us to find those laws, discover them, to formulate that overarching principle that applies to a multitude of situations. That's what a law is. Okay, I call that a physical law is an overarching statement that applies to a multitude of situations. Some of those situations were exemplified last class. Okay. And now let's go ahead. Let's copy the first part of Newton's first law. Example C1, example 1, 2, 3, 4, right? Here you go. That's the first part of Newton's first law. And now I'm going to formulate the second part of Newton's first law. Okay, and it states, okay, you know what? First part, I'm gonna get both side by side here, okay? First part of Newton's first law, okay? I'll just restate them here and then I'll copy it. It's not much difference, the second part. The second part of Newton's first law is not much different. Okay, so, but instead of saying the object is at rest, okay, if we say, if an object is moving with constant velocity, and constant velocity means what? Acceleration equal to 0, then the net force applied to this object is 0. See what changed here? Almost nothing, okay? It's just the condition of the velocity. Here is the velocity, the object is at rest, velocity equal to 0. But here, the velocity is constant. Velocity is not equal to 0. It's the acceleration that is equal to 0. And the net force is still 0. Net force applied to the object is still 0. And don't forget, however, if the net force applied to an object is 0, the object may not, the object may not be moving with constant velocity necessarily, okay? That's what you have to memorize. And those two laws combined, when we combine those two laws, we have the two laws combined become the two laws combined become becomes Newton's first law. Newton's first law of motion. Okay? First law of motion. And I'm going to copy and paste here. If an object is at rest or moving with constant velocity, and then I state here, then the net force applied to this object is 0. Okay, and I'm going to put it here. In this case, the converse is also true. In this case, the converse is also true. Or if the net force applied to an object is 0, the object may be either at rest, or moving with constant velocity. Okay? That's the full statement of Newton's first law. Now, let's go back to our illustrations here and take a look at how this law is illustrated, right? How this law is exemplified and illustrated. Let's see here. I'm going to copy and paste all those illustrations in a new file. So it's well organized for me, right? Go. Okay, new. Oops. Going on here. Okay, now I got it. Here's the first part of Newton's first law. Law. And you saw all of that, the at rest, right? Here's an illustration of the normal force. And this belongs elsewhere. This belongs at the beginning of the slide. Illustration of the normal genetic illustration of the normal force. Okay, and okay, here you go. Genetic illustration of the tension, right? We did an example like that. Go. Velocity is still at 0, but what about now? Second part of Newton's first law. Now we have all those sorts of forces being applied to my object, but the object is moving. It's moving with constant velocity. Okay? We have the normal, we have the weight, we have the tension, and here we have the force of friction again. But because the object is moving, the force of friction has a different name. The force of friction has a name for kinetic force of friction. There is the static force of friction and there's the kinetic force of friction. That's why I put here the K, the subscript K. Okay? So object is moving with, we just example in the slide. Example in the slide. Okay? Going back to the same formulas that I got before. Okay? You go. And I'm going just to okay, so here you go. We're just gonna copy that and paste and adjust it for this specific case of constant velocity. Okay, here you go. Example, I'm gonna call that example 1 of today. Example 1. An object moving with constant velocity over an horizontal surface. An horizontal surface and being pulled by a string of tension T, making an angle theta with the horizontal. Is that what we have here? I gotta illustrate the angle theta here. Here you go. Let's copy that. So I don't have to redraw it over again. There you go. The tension I'm going to put here at the top so it doesn't overlap with my okay, so here we go. Go ahead, draw it in your paper. It's very good, it's very important that you practice it on your own. Write that down there in your paper or your pad. Okay. And now because the object is moving, right? We have a tension, which is the same that we had before. We still have the weight, we still have the normal, but now we have a force of friction here. But like I said, it's the kinetic force of friction. Okay. What's the value of the force? Of the net force? How many forces are being applied to the object? What's the vectorial relation between these forces? You write your vectorial equation into two scalar equations. Okay? Solution. According to the second part of Newton's first law, since the object is moving with constant velocity, comma, its net force must be 0. Okay, so here you go. First part done. First part done. How many forces are being applied to the object? How many forces are being applied? Okay, take a look at the drawing, right? Here you go. 1, 2, 3, and 4. Okay? There are 4 forces. Up. And let's put here how many forces are being applied to the object. And what are these forces, right? 1, 2, 3, 4. There are 4 forces applied to the object. the weight that's always there, the normal, the tension, and the force of kinetic friction. It is kinetic because the object is moving. It is kinetic because the object is moving. If it were at rest, it would be static. Would be the force of static friction. Okay. Item 3. What is the vectorial relation between these forces? Okay. So we go ahead and write that down. Net force is equal to the sum of all the forces. In this case, the N is equal to 4 forces, F1, F2, F3, F4, equal to 0, right? And each one of those forces are going to be the normal, the weight, the tension, and the force of kinetic friction. Substitute the S by K. Here you go. Going back. We didn't finish yet. The vectorial relation between those two forces is this equation that you see right in here. Finally, we are going to look at their components, at this equation's components. Okay? In this case, I made a drawing with the force to the left, this force to the left, and this force to the right, right? So let's say that the x-axis is still to the right. Let's say that x-axis is still to the right. You know? Previously, I provide you an example that those forces the tension was to the right, right? See the difference between the, wait a minute. Okay, let's see. This one that I want. Yeah, previously I put the tension to the right, okay? And the frictional force to the left. But now, and in this new example, I inverted the direction. Let's see. Not this one. Let's see. I start with this one. Let's continue with this one, right? Okay. Let's erase this one here. Here you go. Right? So that's gonna make a difference in the signs of our equation. Okay, so let's go back here. Tension cosine of theta. Tension cosine of theta. I'm going to illustrate the horizontal component of the tension. And I'm going to dash it. Okay. We have to shorten it just a little bit. And then the vertical component is going to be like that. X and Y components. And I can even put, name it Tx, right? And Ty. Get used to this notation. Ty. Going back to my notes, here you go. T cosine of theta. Now we have a negative x hat. because the tension is to the left, right? And my force of friction is going to be to the right. To the right, like that. And it's not static, not subscript static, it's subscript kinetic. Notice that I put a magnitude here. So this number here is going to be positive. And this theta here is less than 90 degrees. So it's going to be positive as well. And the sign of the force is going to come from this sign here in the x hat equation, right? So here you go. Let's continue here. Put everything, put x hat in evidence, just like we do is in regular algebra. And now we take the scalar portion of the vectorial equation and make it equal to 0. And oh, I shouldn't forget about the force of friction, right? Kinetic friction. Here you go. Kinetic friction. Because the object is moving at constant velocity, the x component of the tension must be equal to the force of kinetic friction. And now we repeat here for the y component. Right? Going back to the drawing, don't forget, you gotta practice those drawings. We have the normal is along the positive direction of the y-axis. The weight is along the negative direction of the y-axis. And the ty is along the positive direction of the y-axis. I can even put here my y-axis here, even though I didn't put it. You should be able to imagine that in your head, right? But the correct is to go ahead and so we can put the proper signs for those scalar components. So here you go. Magnitude of the normal along the positive y direction. Magnitude of the weight along the negative y direction. And the tension, the y component of the tension. That's going to be sine of theta, right? If the x component was cosine, the y component of the tension is sine here. Not much different from the other situation, right? And we go ahead, repeat everything that we did before, right? Put the y hat in evidence and equate the scalar part of the equation to 0. The furthest that we can go is this equation right in here. And I'm going to put, okay, the two equations now are, putting the two equations side by side. Equations side by side, we get, okay, this one and this one. Okay, two equations. Okay, a system of two equations. A system of two equations. A system of two equations. Come on. This system can be solved only if you have at most two unknowns. Okay? If you have three unknowns, if you have three unknowns, you won't be able to solve it. won't be able to solve it. Okay. Let us assume, let us assume that only the tension and the normal are the unknowns, and everything else is known, and everything else is known. Okay. So I would say something like that. T has a question mark. Oh. Okay, T has a question mark, right? We do not know T. We do not know N. Let us put like that. The magnitude of the normal is unknown. The magnitude of the tension is unknown. The magnitude of the normal is unknown. Like that. However, you know everything else. Let's assume that only the tension and the normal are the knowns and everything else is known, right? Theta is known. I'm going to put it like that. Theta is known with an exclamation point, right? I use an exclamation point to state that this parameter is known. The magnitude of the force of kinetic friction is known. Not just the magnitude, but also the vector, right? The direction. And the direction of the weight is known. Huh? I call that example 2. Okay? Let us assume that from the problem above, okay? From the problem above, let us assume that only the tension and the normal are the unknowns and everything, only the magnitude, because we know their direction, the magnitude of the tension and the normal are the known, and everything else is known. Right? Find the unknown parameters. Okay. We could have done the same thing here for the previous problem. What we do? Okay, it's going to be kind of a rather easy problem to solve. It's not that difficult at all. Some problems, like those, they are difficult, but this one is not that of a big deal. Note that the force of kinetic friction is known. Theta is also known. The only one that we do not know is the magnitude of the tension. So all we have to do is to solve this equation for tension. Like that, right? And if you want to know what's going to be the normal, all I have to do, here you go, I'm going to bold face the normal, right? Now we know what the tension is because I found it right in here. All I have to do is to replace it right in here. And then solve now for the normal. So normal will be minus this guy here, plus this other guy, right? And then let's commute so it looks better. So the final result looks better. All right? Can you do better than that? Yeah, we have the sine and cosine here, right? Yeah, we can do better than that. Let's simplify as much as we can, but only as much, right? Sine divided by cosine becomes a tangent, okay? And that would be my final results for this problem. If I give you numeric values for those parameters, you would be able to solve for the known parameters, you would be able to solve the known parameters numerically. Okay, let's take a look at the book. Let's take a look at the book where we are here, Wiley plus, and okay, 2D motion. Now I have to schedule the chapter on Newton's law. Okay, so you can, oh, not yet. Let me schedule here a date, and I'm gonna go accordingly to the exam. Chapter 4 is gonna show up in the second exam, so we can schedule it for the 30th of October. Okay, 30th of October. Blah, blah. Okay, available from, I'll put it today. Which today is it 9? Okay, let's see. 12 a.m. Let's save it. Let's see if you get it. And assignment for chapter 4. You have 3 weeks, more or less, a little bit less than 3 weeks. I didn't. Okay, now it is. October 30th, 11:59. Right? October 30th is when? Wednesday. Yeah, Wednesday. So you have 1, 2, 3 weeks. Okay? And do October. That's good. You're in good shape here. Any questions? Am I missing any questions from you? Yeah. So far, no questions, right? 9:26. And let's take a look at the book. So we can situate ourselves where we are. And I also must save my presentation here. Save, browse. Navigating in my computer. Illustration. Newton's laws of motion. We see it's a plural. We have more than one law of motion. You got, and then we can come up with other types of problems. For instance, this one here. This one here. Okay? This one here. We have this object that is initially at rest. That's at rest in this inclined plane. We have a normal, we have a weight, and we have another normal here. That's very cool. 1, 2, 3, 4, 5 forces, right? And I'm going to name it. This one has to be N1. This problem is a little bit more challenging because the object is an inclined plane. Okay, the object is at rest. And let's say this object has a tendency to climb the inclined plane. If the object has a tendency to climb, to move upwards, it means that the force of it will have a force of static friction that's going to be downwards. Okay, and I gotta put how also I also have to put a theta angle here. Let's get that theta angle. Even better, I'm gonna get another one. Make my life easier. Mhm. Surprise, surprise. I can't find it. Okay. I'll have to. Oh, here you go. That's the one I was looking for. Good. Like that. Like that. Like that. No, no, no. Sorry. That's not what I mean. I meant the plane, right? Incline the plane. Here you go. Yeah, but we need that too, right? We need those. This one, and we need the other. Theta. We need, oops. We need those two angles here. One angle is going to document the angle of the plane. There you go. And the other angle is going to document the angle that the tension makes with the horizontal. Like that. Without those parameters, we cannot solve the problem. Here you go. And instead of calling it theta, I'm going to call it theta prime because it's a different. No, it's not. Okay, I'm going to call it theta 1 since I am not. It could have been v greater than 0 as well, okay? If you're, and then I will do it climbing the plane. Okay. So we repeat what we have done for the others, okay? So another challenging example. Challenging example, okay? Example 3. Consider an object of mass m at rest on the top of an inclined plane, making an angle theta 1 with the horizontal. Symbol. The horizontal. Here you go. In addition to the regular forces, comma, we also have two additional forces. Additional forces, a tension, making an angle, a tension, making an angle theta with the horizontal, making an angle theta with the horizontal, and a force normal to the left side of the block, which I call N2. Okay? So we are going to repeat exactly what we did before here. Right? So here you go. And let me just copy this thing here. I have to change it. Right? Here you go. Repeating the enunciate of the problem. Okay. First, what's the value of the net force? Right? How many forces are being applied to the object and what are these forces? Okay. What is the vectorial relation between these forces? Here, write your vectorial equation in two as, right? As two scalar equations. Okay? Because the object is at rest, we use Newton's law of motion. First, we use not even second part. According to Newton's law of motion, Newton's first law of motion. Remember, I combined the first and second part of first Newton laws into a single law, right? Since the object is at rest, right? Its net force must be zero. Or, okay. In addition, okay, in addition to the regular forces, weight, normal, and force of the static friction, the problem states that there are two more forces that there are state that there are two more forces applied to the object. A tension and another normal, someone pushing the object, okay? Applied to the left side of the object. Okay? Other forces applied to the object, a tension and another normal force applied to the left side of the object. a total of 5 forces. A total of 5 forces. Now we have to get the vectorial relation for these forces. What's the vectorial relation between these forces? According to this example, we have 5 forces applied to this object. And their summation must be 0. Must be 0. Because the object is at rest. Oh my goodness, is at rest. I need to buy a better keyboard. Or, net force is equal to 0, but now n is equal to 5. We have to add a 5th force here in the summation, right? And this normal is going to be, let's see what, how I stated as N1, right? We have N1 here, and you have N2 there. Here you go. We're going to have N1. We're going to have N2. And because the object at rest is the force of static friction equal to 0. I will copy all this vectorial summation and put it here. Right? And now we have to go the most challenging one, right? The most challenging part of the problem, of the example, is to write your vectorial form equation as to a scalar equation, okay? Making, I'm gonna put it, making a okay? I have to state that we know angle theta 1 and another non-angle theta. So here we go. So now x component. Let's look at the x component. You have always to consult the drawing. We're going to be drawing lots of things here. Let's say in this case, let's make our x-axis in a different direction. Okay? It's very convenient for this type of problem to put my axis along the inclined plane. And if you put the x-axis along the inclined plane, the y-axis will have to be perpendicular to this inclined plane, okay? We can choose our axis to be whatever direction we choose. I could have but I have done this one here. I have chosen this direction here because make it easier for us to solve the problem. But if you want, you can repeat this problem for the axis, x-axis in the horizontal direction and y-axis in the vertical direction. No problem here. Okay? And now, here you go. Let's go for my x components. And I will do this ball. I'm going to put it side by side. Okay, here you go. So I don't have to keep on shifting from page to page. X component. X component is going to be, X component of the tension is going to be cosine of theta minus theta 1. Do you see that? Theta 1. You see that? and my x direction in the positive x direction, according to my axis. Start with the tension. Okay, we are projecting my tension parallel to this direction. And this direction is going to be theta minus theta 1. What else we're going to do? Okay, we are going to write down the contribution of the force of friction, which is the force of static friction, which is along the negative direction of the x-axis. My normal, my second normal, is going to be along the positive direction. See that? The positive direction. I'm going to put that here. My normal 2. Oh. Normal 2. What else? What else can we put here in the x direction, okay? And notice that this normal 5 forces, right? So far we came up with 3, 1, 2, and 3. Notice that this normal here, this other normal, is perpendicular to the x-axis. Consequently, its component is going to be 0. But what about this weight? Okay, what about this weight? Because we chose a different referential frame with an inclination, this weight is going to have a horizontal and vertical component, a y component and a not horizontal, right? But let's see, a horizontal and not horizontal. Sorry, hey, my goodness, a y component and a x component, like that. Make sure I'm going to dash all those things so you have the proper picture of those components. Okay? So what I'm going to do here, notice that the x component of the weight is along the negative direction of the x-axis. Okay? And I'm going to do the following. I am going to put Wx component with a negative sign here, magnitude of the Wx component, and then we worry about how it's going to be written down. Okay? Did you get it? And we're going to go down for the y component. I'm going to erase this one here. We don't need any more, otherwise it's going to cause some confusion, right? And let's worry about the y components. For now, I'm writing down just the x component of the weight. Okay, but I'm going to get back to that and show you exactly how it looks like, how it can be written down. 9:47, we're almost getting to our break. Let's solve this one here. Now, y components. Okay, we have the tension has a y component. Okay, I'm going to, and this y component is going to be given in terms of those angles, theta minus theta 1, right? The sign is positive because the y component points along the positive y direction. Which one next? Which one is next? The static force of friction doesn't have a y component whatsoever, right? It has only a x component, so you don't have to worry about that. then we have to worry about this other normal force. Someone is putting their hand there, propelling the block upwards, preventing it from sliding down, right? But again, this other force doesn't have any vertical component whatsoever. So it's going to be another zero here. I'm going to put it here, plus zero, right? Which else? Okay, now we gotta go for my weight. The weight has a vertical component. The weight has a vertical component, and this vertical component points along the negative direction of the y-axis. Oh, and by the way, that's not y-x hat, right? This is y hat. Here you go. Minus wx and y hat. And finally, 1, 2, 3, 4 forces, the final force that has components along the y direction only. I am going to take advantage, and the positive direction of the y direction, the positive direction of the y-axis. I'm going to take advantage of this equation here and change to n1 and y hat. Y hat. Okay. Let's continue solving this problem. What do we want to do? We're so busy trying to solve this. Here, write your vectorial equation as two scalar equations. Okay? And let's go ahead. Let's just repeat what we did before. Now the x hat can be placed in evidence. When I place the x hat in evidence, all these other x hats disappear from my equation. And we have to worry about this guy now. Okay? Wx. We have the mass of the block. And let's see here. I'm gonna move away. You have to know which angle is this one right in here. And also which angle is this other one here. Okay? You have to analyze the situation very carefully. And this is basically a problem of geometry. That's what it is. Okay? And there is a rather easy way of seeing that. Suppose that this plane was in the horizontal, right? Suppose that this plane was in the horizontal direction. If the plane were in the horizontal direction, this angle here would end up being zero, right? Now, if we raise this plane little by little, this angle is going to increase little by little. Similarly, if this plane were in the horizontal, right? This angle here would end up being 90 degrees. And again, if we increase the plane little by little, this angle would increase, but this angle would decrease from 90 degrees to something else. So what we have here, we have a theta 1, this angle here, theta 1 angle, right in here, in this right angle triangle. And we want to get the x component of this weight, which should be a weight W sine of theta 1, okay? So I'm gonna write that down here. Weight is W sine of theta 1. Let's continue working here. So here you go. Don't forget I provided you with the mass of the object. Consequently, this weight here can be changed to mg. Okay. And I want to get our scalar equation. We get the scalar equation by eliminating the vector x hat. Can we do better than that? Yeah, we can pass whatever is negative to the other side, right? That's the best thing we can do. Pass the negative terms to the other side of the equation. And we end up with this relationship that relates all those parameters. And we can do the same thing here for the y component. Let's finish the y component, then we go in our break. Okay, I don't need the zeros anymore. The y component is going to be written in a similar fashion as the x component, but instead of sine, it's going to be cosine. It's still a y hat. Okay, we factor the y hat in this vectorial equation. Erase, erase. And finally, we get our scalar equation. That's going to be given by something like that. We pass the negative terms to the other side. And we have this relationship between the parameters. Repeating what we did before, putting those two equations side by side, right? One next to the other. We have a system of two equations. Just like before, more complicated than the other because of the different forces and the plane that is inclined, okay? Theta minus theta 1. Oh, yeah. Okay, thank you. Let's see. Just seeing here your messages, right? Why is tension not part of the regular forces? I thought friction and tension were both part of the regular forces because they counter one another. Okay, okay. Why is that? Why is that? By regular forces, I mean the forces that are always there. That's what I mean. Okay? That's what I mean by regular forces. The weight is always there. The weight is always there. If the mass is in contact with the surface, then the normal is going to be there as well. Always going to be there. What is not always going to be necessarily there is going to be the tension and this other normal. Okay, that's what I meant by regular forces. By regular forces, and the force of friction also is always going to be there unless you're playing with a frictionless surface. Okay, so that's what I mean by regular forces. That's what I mean by regular forces. The forces that are usually always there. Okay, this tension might not be always there unless I state it to you. Okay, this normal may not be always there, but everything else will be there because we have a surface and you have a friction between the object and the surface. Okay, and why is it theta? All right, theta 1 and theta minus theta 1, right? Why is it theta? Okay, so let's take a look here at the drawing, right? I'm going to do the following. Take a look, and I'm going to copy There's a very easy way of illustrate that. I am going to put, no, it didn't work. Let's try it again. I'm going to overlap the x-axis, right? And I need one more thing here. Here you go, this one, and this one. Oh, not this one. Ay. Okay, I gave up. Let's do it again. The best way of explaining that, Molly, is in this way that I'm doing, okay? Let's see here. Okay, so I need now to copy, you know what? I'm gonna use this one. Someone is trying to get in. Okay, and here you go. Are you following, Molly? Here you go. This is theta 1, right? I'm just translocating the angle to another place. I'm going to put theta 1 red here. Okay, and what do we want to find out? We want to find out this component of the tension. See that? That's the component of the tension that we want to find out. I'm going to duplicate this drawing, and I will erase this one here so it doesn't get very busy, right? And go back to this one here. Okay? Did you get that? No? Do you see that now, Molly?
Yes, thank you.
Make a huge difference, right? When we do something like that, right? Okay, and if I take too long to answer your questions, please feel free to talk through your mic. Okay, sometimes I don't see your messages here in the chat window. Okay, so let's see, 10:01 right now. Here are the. So that's the type of problem that we are going to be solving, okay? Some problems are more complicated than others. Some problem has more forces than others. And some problems can even have a three-dimensional component of the force, okay? In real life, we do get that a force with three components in the three-dimensional spaces. But here in this course, in general, we are using only two dimensions. Two dimensions that are going to generate only two scalar equations. Okay? And we solve, in order to solve this system of equations, we have to know what's known and what is unknown, okay? We have to know what, and to solve this system of equations, we must have only two unknowns. Two equations, two unknowns, we solve the equations. Two equations, three unknowns, we cannot solve the system. We cannot solve the system of equations, okay? A system of two equations, this system can be solved only if you have at most two unknowns. You have three unknowns, you won't be able to solve it. Okay, now any questions? Any more questions? So let's get the, while you think about that question to make me, I will get my spreadsheet here and take attendance. Let's see, Audrey Aguilar. Thank you, Audrey. One attending. Matthew. Are you there, Matthew? I don't see Matthew here. Yeah, he's coming, right? Brianna Carrillo. Thank you, Brianna. One more, Jazzy Castellano. Thank you, Jesse. Gabriel Contreras. I don't see Contreras. Yeah, Contreras seems to be here, but it looks like she's away from the computer. Let's put a star. Liliana Cortez.
Here.
Thank you. Juan Salvador Escalera. Hello, Juan. Okay, Molly is she's definitely here. This doesn't even have to respond, right? Here you go. Henry Kim.
Here.
Thank you, Henry. Ruth Mandujano.
Here.
Okay, Noemi Martinez. I don't see Noemi here. Yeah, I don't see it. I have 21 students. Danae Miller. Ramon Olivares. I don't see Ramon here in my list. Taylor?
I'm here.
Okay. Alexis. Alexis, I believe Alexis dropped. Yeah, Alexis dropped. So we can take him out from here. Put here at the bottom. Stephanie Ramos. Hello, Stephanie. Stephanie is in my roster, my Zoom roster, but looks like she's away from the computer. Jeremiah Reyes. Thank you. Sha Rosario.
Here.
Okay, thank you. Ali Standard. Okay, Ali is here. Jason Strait.
I'm here.
Thank you, Jason. Elena Trujillo.
Here.
Thank you. Jason Valadares.
Here.
Stephen Vathapali. Stephen, are you there? Okay, Stephen is not answering. And next is going to be Laurel Williams. I don't see Laurel there. Nuhamin Wanimu. Okay, thank you. Alia Zavala. Okay, so 3 students didn't answer. And let's see how many we have here. 18, 21 students. Yeah, we have the numbers match. 3 students who didn't answer, sum to 18, we get 21 here in my Zoom roster. 10:07. Now is time for our break. If you don't have any question, break from 10:07. Okay, Gabriel. Okay, let me write it down here first, and then let's see, 10:07 a.m. to 10:22 a.m. Right? Gabriel Contreras, right? Okay, good. 19. So let's take our break now, and I see you in 15 minutes. Stop sharing. I am back. And let's see how is the situation of the groups, right? Mhm. Stephen, are you there, Stephen? Fathapali? Vathapali? I believe that Ramon, are you there?
Yes, I'm
I
here.
don't know if you called me. Sorry.
What's your name?
Stephanie? Ramos?
Stephanie?
Yes. Other.
What was the last name?
Ramos?
Ramos, Stephanie Ramos. Okay. Stephanie Ramos. Okay. And what do we have now? 21. Okay. Looks like someone left. Okay. And okay. Lab. I'm going to put here freeze pane. Freeze pane. Let's see. Nuhamin, do you have a group, Nuhamin? You have a,
No.
no, right? Let me see what we have here. 1, 2, 3, 4, 5 people in group 2. Okay. So let's see. We have 1, 2, 3, 4, 1, 2, 3, 4. Okay, group 1 has only 3 students. Why don't you join them? Okay,
Okay.
let's do that. Get in touch with them, Matthew, Jesse, and Gabriel. Would you like to welcome Nohamin to your group? Okay. Exchange, contact information, right? And we'll be moving. Let's see. Audrey Aguilar, yeah. Okay, and let's go get my spreadsheet and let's see. Group 1. Yeah, right in here. What you can do, Nohamin, you can contact your group members through Canvas, okay? And vice versa. So just get their names and you'll be able to email them. You will need, let's see, Nohamin, you're going to need the link to your group folder, to group folder number 1. Ask them to provide you the link to group folder number 1, okay? And you'll be able to access the material that I upload there to the group. Today experiment is accelerated motion. Today's experiment is accelerated motion, the inclined plane. Inclined plane, okay? The inclined plane is a classical experiment in physics. It's a classical experiment in physics. It seems that it was Galileo Galilei who was the first one to perform those experiments. It seems it was Galileo Galilei who first performed this experiment. At that time, we didn't have reliable clocks. At that time, we didn't have the technology that we have today. We didn't have we as a civilization, human civilization, we didn't have photo sensors, okay? And Galileo had to make do with whatever he could do with the technology of the time, with the technology and the skills of the time. The idea goes that he managed to measure how long it took for a ball to move an inclined plane just by listening to the bells that he put away along the way of the ball, and that bell would be activated every time that the ball would pass a given point. Because Galilei was trained in music, he could, in a very reliable fashion, find out how much time passed between each bells along the way of the inclined plane, okay? That's how the story goes. One day I would like to go to Italy to visit his museum and find out more about his work. One of the giants in physics. Okay, and among others, right? Okay, but let's get your spreadsheet and P37 lab number 2. Let's make sure everything is working fine. As you can see, I have several spreadsheets here. Yeah, that looks clean enough to me. 9, 1. Let's start with 1, easier. Okay, that looks fine enough for me. 2. I will walk you through this experiment so you can picture that in your head, how this whole experiment is performed. Ideally, you should be performing this experiment in the classroom, in the lab room, or even better, if you had all the toys, right, we could ship to your house and you would perform this experiment. In my country, in Brazil, that's exactly what they do. It's amazing that they can have so much stuff and ship to the house of the students to perform for the student to perform the experiment. Okay, 4, that's 8. Let's see, 5. 5. How many groups do we have? Going back here, we have 6 groups. Okay, we need one more spreadsheet. This one here. Okay, and just in case, 7, 10. Okay, now see. Oh. Okay. Later. Group 1. You have your spreadsheet there. Group 2. You have your spreadsheet there. Group 3. Spreadsheet. Group 4. Spreadsheet. Group 5. Spreadsheet. Group 6. Spreadsheet. And copies. Making copies of those spreadsheets. Go ahead. Download the spreadsheet to your hard drive. Okay. Just a reminder. Here we go. Report for lab 1 is due, right? Please upload your Excel spreadsheet, not the Word document yet. We're going to do that later on into your folder, into your group folder. Just one spreadsheet, just one spreadsheet per group. Okay, so it must be those spreadsheet must be written down just like that. P06L01, right, for lab 1, GXX, and then you put your 2-digit group number here, and you do the same for the lab number 2, P06L02G01, 01, 02, 03, and so on, right? So uniformly accelerated motion. Everybody got I want to hear from you. Everybody got the spreadsheet? Let me give you a little bit of time.
Yeah, I got it. Group 3.
Okay. And I'm going to get my let's see. Lab manual. Let's see. Okay, right in here. Nope. Accelerated motion right in here. Okay. So let me walk step by step how this experiment is performed in real life. Okay. We start with one of those tables that we have in the classroom. And, you know, the first piece of equipment is an air track. This air track is a 2-meter long track made of aluminum. It's hollow on the inside and full of holes throughout its length, along its length. Okay, there's a reason why it's hollow. There's a reason why we have all those holes along its length. And they're going to become apparent very soon. It has a nozzle as well at the end. And there is a reason why we have a nozzle. Okay. And it has two legs. The distance between the two legs is the distance that's documented there in your spreadsheet B. Let's take a look. It's around 1 meter. Okay. So let's see here. I'll get this copy. We need this parameter B right in here. Okay. B is 0.996 meters. So that's your first measurement. That's your first measurement. Going back here to my uniform accelerated motion. Okay. In this experiment, we use the following equipment. By the way, this air track is very similar to that air table that we have at the arcade. Okay, here you go. This air track here is very similar to very similar to the hockey table that you have at an arcade. The hockey table has holes throughout this entire area, and through those holes, pressurized air is pumped through to levitate your hockey puck, right? Your puck. And why do we do that? Just to decrease the friction between the puck and the table. We do the same here in this air track. We pump air through the nozzle that goes through those holes in the air track to levitate our cart that we use in this table, in this experiment. The distance B is measured with the ruler. And at this point in time, you already know that the resolution of the ruler is 1 millimeter or 0.001. Okay. The air track has a nozzle, air track with a nozzle, right? With a nozzle. And then we also have a hose. I provide a hose to my students. Okay, here's the hose that is coupled into the nozzle. Hose. The hose is coupled into the nozzle of the air track. And then what else do we have? Then we have an air pump. The air pump is going to blow the air through the hose, through the nozzle, and into the air track, into the hollow air track. Hollow air track with hose and a nozzle. So, just like I said, the air track behaves just like your hockey table at the arcade. Let's take a look at the hose here and the pump. Okay, the pump is connected to electricity and it's a very noisy device. Okay. Next, we have a glider, a little cart that fit into the air track. The air track has a triangular cross section. Let's write it down there. The air track hollow air track with a triangular cross section and holes. With holes and a nozzle at its end. Okay? And the glider, which is the cart, fits perfectly into this triangular cross section of the track. Okay. The glider has a length L, which is also measured with the ruler. We need this length to determine the speed of the glider on the track, along the track. So let's take a look at their spreadsheet. Locate the length of the glider. Here you go. Here's the distance between the legs of the air track, and L is the length of the glider. It's approximately 12 centimeters long, 13 centimeters long. Okay? Can you picture that? You know, make-believe experiment, right? Length of the cart. What do you do in this experiment? We go ahead, I provide you with a shim. This shim has a thickness. It's like a small rod, a short rod of length or thickness H. And we use the shim to raise one end of the track. Let us take a look at the H. Right in here, H is also measured, but not with the ruler. It's measured with the micrometer, okay? And because it's measured with the micrometer, we can display it with more significant figures, right? In part, it's measured with the micrometer. So a micrometer is provided as well. Remember, memorize it, that the resolution of the micrometer is 1/100th of a millimeter, or 5 decimal places in meters. Let's take a look. Here you go. P, L, and H. You're going to need the acceleration of gravity for comparison purposes. Okay. In this experiment, okay, let me write it down. In this experiment, you will measure, you determine, okay, measure now, you determine the acceleration of the cart, and this acceleration will be used to determine the acceleration of gravity, G. Okay? And I'll explain to you how we do that. Okay, micrometer. Then what else? We're going to use a photo gate. Galileo didn't have a photo gate at his time. This technology was still, let's say, 300, 400 years away from him. What is the photo gate? The photo gate is a timer. It's a stopwatch with a resolution of 1/10 of a millisecond. It's a timer, comma, a stopwatch with a resolution of 1/10 of a millisecond. 1/10 of a millisecond is 4 decimal places in seconds as well. And let me show you a picture of a photogate so you can have photogate timer. Fences and timers. Pasco has, we use Pasco's photogates there at the college. Let's see. Here you go. That's how they look like. You know, it's like a little jar with a gap in between. Okay. And then we can put at the side of the air track. That's not the air track that we have. Let's see. Smart gate. Okay, here you go. That's the one we use. Accessory photo gate. And we use those two. This is an accessory photo gate, and this is a photo gate timer. Here, the photo gate timer used in conjunction with the accessory, with this accessory. Let's take a look at the picture, okay? Our photo gate looks exactly like this one here, okay? Here's a screen, LCD screen that displays the amount of time that it takes for an object to cross this photo gate, this little jar here. Okay, that's how it looks like. This photo gate can be used in conjunction with this accessory photo gate. Look at the shape, it's exactly the same. What you have here is exactly the same as this device here. This device doesn't need this whole setup here. Why is that? Because it can be connected to the main photo gate. And the resolution, again, is 0.1 milliseconds, 0.0001 seconds. Going back to the notes. The timer, a stopwatch. And how does the photo gate works? Okay, here you go. Oh, first, what's their components? Okay, the photo gate has a infrared LED. Infrared LED. Okay, and I'm going to show you this infrared LED. Okay, this on the inside of this little jar, you have the infrared LED. On the other side, you have a detector, okay? Infrared detector, light detector. It's possible to, it's very similar to your remote control at home, okay? Your remote control at home to turn on and off the TV also has a infrared LED, a light source that emits the infrared light ray. And on the TV, you have the detector. And that detector is programmed to recognize different commands of your remote. Okay? When an object crosses this beam, so here you go. You have a light beam being emitted from here to here. Okay? When this light is on, when the detector receives the light from the LED, it doesn't do anything. The moment you put your hand or an object in between those two objects, the LED and the detector, it starts to time. The clock starts to run. You take out your hand, the clock stops. It uses, like I said, the photo gate timer. It uses the LED light as a timekeeping mechanism. Going back here. Infrared LED, a photodiode is sensitive to the infrared LED. and an LED, a red LED indicator. When the beam of light between the infrared LED and photodiode is interrupted, the red LED turns on. It also has a red LED as it's just like an indicator. The red LED is this one right here in front of the photo gate. It lights up to tell the operator that the photo gate is timing the event. Okay, next. Let's take a look here. Not this one, this one. I'm gonna put here my cart, right? My cart is going downhill. Here's my x-axis. And here's my photo gate timer. I put my photo gate somewhere down the stream, downstream the air track. You do not want this photo gate too close to the end, but you don't want too far away either. Okay, and a good place to put your photo gate would be close to this leg here. This position of the photo gate, I call it position Y. Okay, and in the experiment, we perform a series of measurements of the position of the photo gate. And that's what this table here is all about. First table, we covered the first table. Now we're going to cover this table here. See here? Position Y, what's the unit for Y? Unit of position is, right? In the International System of Units, you should put it there. So what we did here, we perform an experiment to find out this position Y 5 times. 1, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5. We sum all those positions, and don't forget, and this position Y, by the way, is measured with the ruler. Y measurements measure is the tape, which has a resolution similar to the ruler. The tape attached to the air track, 1 millimeter or 0.001 meters. We take 5 measurements of Y using the photo gate and the cart. Okay, so here you go. This measurement must have 3 decimal places. This measurement must have 3 decimal places, and so on, right? And this measurement here will also have the sum of all those, not this measurement, but this result here will also have. We also end up having 3 decimal places, but very important, it may end up having more significant figures compared to the other. It's all going to depend on the summation value here that we get. Because those numbers are 0.2, 0.2, and so on, I suspect 1, 2, 3, yeah, this measurement is going to have more significant figures than the other. This result is going to have more significant figures than the others. Okay? And then we take the average. What do? We put the photo gate at a fixed position. Don't change anything in the photo gate position, but get your cart, and little by little you approach the photo gate. When the red LED light of the photo gate turns on, it means that the cart is crossing the light, the invisible light beam that's emitted by this photo gate. At this point, you stop your cart and look at the front bumper. What is the position of the cart in this ruler, in this tape that's attached to the air track? And we do that 5 times. That's what it's all about. Next is the actual experiment. So those are just preparations. Preparation for the actual experiment. Let's put that like that. Preparation for the actual experiment. Let's see. I'm going to do like that. Here we go. Yeah, and do it differently. Okay, doing it differently, organizing it differently to become more user-friendly. Air pump, glider. I want you to study this, okay? For the exam, shim, micrometer, photo gate, and then explanation of the photo gate. Okay, here we go. Photodiode. And then actual experiment. Preparation for this one goes right in here. E. Oh, that's not good. Supposed to be J. Yep. Okay. Setting numbering value, J. Sometimes Microsoft Word doesn't do everything that you need it to do. And now, next, the actual experiment. Okay, first, we bring the car to this highest position on the track. Right in here, highest position on the track. We have the cart crosses the photo gate, which produces a time measurement of how long it took for the cart to cross it. Okay, so think about that. We release the cart from rest, and it crosses the photo gate. The speed of the cart at this point in the photo gate is going to be the length of the cart divided by the timer, the time measured by the photo gate. Okay. The speed, okay, I produce a time measurement T, okay. The speed of the cart being L divided by T. So far we have the following measurements: LBH, TX, X is the initial position of the cart, Y1, Y2, Y3, Y4, Y5. Let me put that, show that again. Here you go. X is this position right here. Y is this the position of the photo gate. What we're going to do, we're going to release the cart from different heights along this ruler. This air track. The higher the cart goes, the faster it's gonna move through the photo gate. Okay. Okay. Y measurement that I already talked about. Oops. Let's see. I'm supposed to be here. Okay, here you go. We have now the following result. Here you go. Y and the D, the distance between the cart and the photo gate. Let's see if we have here. Let's see here. Here the cart going through the photo gate, right? Yeah, And D is going to be y minus x. Y minus x. Let's go to our spreadsheet again. Here you go. Here's my t, here's my x. Okay, the higher we release the cart, the faster it moves through the photo gate. My d is the position of the cart minus the position of the photo gate. Right here. Don't forget the resolution of the photo gate, 1 millisecond, right? 4 decimal places. 1 millisecond is 4 decimal places. Here's the measurement of the position of the cart, which is going to be also done with the tape, metric tape with 3 decimal places. And then here you have to subtract one measurement from the other one and apply the rule of subtraction to determine the number of sequence figures. Okay? The velocity of the cart is going to be the length of the cart divided by the time measured by the photo gate. And then, we are going to need this square of the velocity as well. Don't forget to fill up all the units right here. And what are we going to do with the square of the velocities, right? Let's see, do we have any questions so far? 11:05. I think we should take a break right now. I want you to think about that, what we are going to do with the velocity square. Recall that there is a formula that involves the velocity square, right? Of an accelerated object. But we'll talk more about that in 15 minutes. Any questions before we go for the break? Okay, so here we go. Break from 11:05 a.m. to 11:20 a.m. So I see you in 15 minutes. I'm back here. So here you go. Here are the measurements and here are the results, right? Why do we get this v square? Why do we get this v? Okay, so what we are going to do here, we are going to use that formula that we derived before, okay? And the equation that we derived in class is this one here. Do you remember this equation? Here you go. I'm going to put in the actual format that we used in the classroom. Okay, delta x. In this case, delta x is equal to the d that is in the spreadsheet. Okay, here you go. Where delta x is equal to d. So what we're going to do, the initial velocity, we release the cart from rest is 0. Consequently, the formula becomes simpler. And what we're going to do, we are going to plot v squared along the y-axis and d along the x-axis. That's the first graph, the first and only graph that you have to plot, okay? So I'm going to do a plot here so you can see. You go v squared d, okay? According to this equation here. V squared should be linear with delta x or d. Let's see if we get this linearity relationship. Insert. Okay, oh, nice, isn't that? And we're releasing the card from different positions, okay? Just to clarify again, we release it from here, then we release a little bit from here, and so on. Okay, that's how we connect we get all this data that you see in there. We're going to add the trend line. Here you go. That's my acceleration. Oh, wait a minute. This is V. This is V square, right? This is V square. Here is 2A delta X. Okay? This X is delta X, 2A delta X. So what you see right here is in reality the acceleration divided by 2. The acceleration divided by 2. 0.2621. So let's go through every one to make sure everybody is prepared and has everything that you need. Okay. Spreadsheet. Okay, Nohamin, Wandibu, did you get this? Did you download the spreadsheet, Nohamin? Oh. Let's see, we have, yes, okay, good. So Matthew is here. No, Matthew is not here. Jazzy Castellano. Okay, do you have the, Harry's telling me he doesn't have the spreadsheet. Do you have the link for your group folder, Henry?
Yes, I do.
Okay, so just access the link and download your spreadsheet. Were you able to do that?
Let's see.
Okay, keep me posted. Okay, let me go
Okay.
next here to Gabriel. Gabriel, did you download the spreadsheet, Gabriel? Yes, good. Next is Liliana. Did you download the spreadsheet?
Yes.
Okay, thank you. Juan Escalera, did you download the spreadsheet? Look like Juan left, huh? I'm gonna put a little O here to remind me that he's not in the classroom. Molly, did you download the spreadsheet?
Yes.
Okay, Henry, did you manage to download the spreadsheet?
Not yet. Sorry.
Do
Still
you have the
looking.
link?
I do have the link. I'm trying to find where it's at. I don't see
Okay,
any.
so let's see if I can help you. Na, 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 na. Let's see if I can help you. Right in here,
I'll
you're
never.
number 2,
I found
right?
it. Sorry.
You found
Sorry.
it?
I found.
Okay.
Yeah. Thanks.
Yeah. There's a bunch of stuff here we have to
On the way bottom, right? Yeah.
at the
That
very
one.
bottom.
Yeah. Thanks.
Center you. Okay. Next, let's see. Larell Williams. Larell is not here. Ruth, are you there, Ruth? I don't see Ruth. She was here before, huh? Ruth. Okay, so now it's 0. And Noemi Martinez. No. Danae Miller.
Yes, I
Yeah.
downloaded.
Okay, thank you. Ramon Olivares.
Yeah, I got it too.
Okay. Taylor Farm.
Yes.
Okay, thank you. Stephanie Ramos.
I'm in the middle of doing that.
I'm sorry, I didn't hear you.
Oh, I'm in the middle of doing it, but yes, in the process.
Okay, good. Okay, thank you. Jeremiah. Hello, Jeremiah. Okay, I don't hear from Jeremiah. And let's put over here. Sean. Did you manage to download the spreadsheet?
I'm trying to do that right now.
Okay, so I'm gonna put working. Okay, W for working. Jason Straight.
Yeah, I got it right now.
Okay. Brianna, let's see, Carrillo. So I was away from my screen, but yes, I downloaded. Okay, Brianna. Which group are you, Brianna? Group 6. Okay, I will get to you. Elena Trujillo.
Yeah, I got it.
Okay, good. Jason Valadares.
Yeah, I got it.
Good. Stephen Vathapali.
I'm currently working on it right now.
Working. Okay, so you did download and you are present. Okay. Audrey Aguilar. Yes, good. Brianna Carrillo. Downloaded. Okay, Brianna already told me she downloaded. Ali Standard. Okay. And Alia Zavala. Okay, good. Most of you have downloaded. Let me do a little bit of something here. Yeah. Okay, just get. Oops. Something wrong here. Strange. Huh. Very strange. If equal to, let's do different here. 0, otherwise 1. Better. "19 students, so 3 students are away." Okay, let's keep on checking. And now 11:30, we have another half an hour to go. Okay, plot v square along the y-axis and d along the x-axis. Like I said before, slope is twice the acceleration. Calculate acceleration of the cart. And how do we calculate the acceleration of the cart? We calculate the acceleration of the cart by getting this slope here, 2621, and placing right in here, right? 0.2621, right? Here you go, 2621. Yeah, that's good. And it calculates the acceleration. Acceleration is half of the slope. And then there is a relationship between the acceleration of gravity and the acceleration of the cart. Okay, there's a very nice formula that's given by what you see right here. F67 is A, H17 is B, A for acceleration, right? So, and F17 is have 17 is h. Right here, b divided by h. Okay. Acceleration of the cart, the acceleration of gravity. Slope is twice the acceleration. Here you go. So here you go. Acceleration is half of the slope. Divide by 2. Calculate the acceleration of the cart. Use the acceleration to get the acceleration of gravity. And the acceleration of gravity is going to be A times B divided by H. Okay? So you know the acceleration of gravity is close to 9.8 meters per second squared. And in this specific case, I'm getting 10 meters per second squared. So it is around 3% difference. Okay? So the steps, steps are the following. Again, the steps. Steps. 1. Plot b squared versus d. Two. Log the slope into the last table. Right? Check the percentage difference for the acceleration of gravity. Experimental value for the experimental value for the acceleration of gravity. Then, fill up the units. In the tables. Display the proper number of significant figures. Find the CL. Okay. So at this point of time, I believe you have already plotted your graphs, right? So let's start with those students. Let's see, right in here. Juan Escalera. Are you back, Juan Escalera? Juan is not here anymore. Let's see, another student here. Ruth, are you there, Ruth? Huh, Ruth left for good, huh? Juan Escalera is still here, right? No, Ruth, Juan Escalera also left for good. Okay, let's put it here. And another one here. Jeremiah, are you there, Jeremiah? Okay, he's still here. Okay, good. So did you download their spreadsheet? You managed to download the spreadsheet, Jeremiah? Okay, did you plot the graph? Plot graph, yes, okay. So Jeremiah, where is here? Okay, now anybody else? Sean, did you download the spreadsheet, Sean?
Yes.
Okay, did you plot the graph?
Yes.
Okay, good. So now let's go here back to Nuhamin Ondibu. Did you manage to plot the graph? Hello, Nuhamin. Okay, I don't hear from Nuhamin, so I'm gonna put a little O here. Matthew is still not here. Let's go to someone else in group 2. Molly, did you plot the graphs?
Yes.
Graph, right? Just one.
Yeah, just one.
What percentage difference are you getting for the acceleration of gravity? Right? Before you can give me this result, first you gotta log in the slope, right? Did you log in the slope?
Yes.
Okay.
The slope I got, do you want 0.2288?
0.2288. And what are you getting here for the percentage difference?
9.0851.
Okay, 9.85. Okay. Molly. Fitzgerald. Wait. 9.85, right? Percent. 85%.
0851.
851. Okay, good.
0851.
0.851. Okay.
Yeah.
9.085. Okay, that's good. Less than 10%. We are in good shape here. And let's go for someone in group 3. 1140. Ramon, what's the percentage difference you're getting for the acceleration of gravity?
2.6621.
Okay, 2.66. Not sure you did correctly. Okay, Gabriela is. Do you need any help, Gabriel? See. So, do you need any help, Gabriel? Are you there? Okay, so I'll get back to you soon. Okay, Gabriel? And I don't hear you. If you're talking to me, I don't hear you. Let's go to someone in group number 4, Stephanie Ramos. Did you get the percentage difference for the acceleration of gravity, Gabriel? Stephanie? Not yet? Okay, did you get at least, did you plot the graph at least? Didn't ask you if you plot the graph, right? I should have asked you if you plot the graph. Hello, Stephanie, did you plot the graph? Just one graph. Okay, let's move on to another student. I'm doing that right now. Okay, I'm having problems with my, okay. Thank you for letting me know. So I'm gonna put here you're working on that. And let's see, someone in group number 5. Here you go. Elena, did you plot your graph, Elena?
I have not yet, but I'm working on it.
Okay, I'll put here working. Now, someone in group 6, Ali is standard. Hello, Ali. Can you hear me? Okay, so I'm going to, I don't hear from Ali. I'm gonna put here an O. And Alia, did you plot your graph, Alia?
Yeah, I plotted the graph.
Uh-huh.
The for the slope, I got 0.2157.
Wow. 2157, that's good percentage. Okay, that's great.
But
And yeah,
for the percentage slot that you were mentioning, it says 18.4807.
oh, 18.4, that's
So
the
I don't
percentage
know if
difference. Okay.
it's okay with that.
Yeah, okay. So your group number 6. Let me take a look here at the spreadsheet of group number 6. Kind of a little bit on the high side, 18%. But definitely it's not your fault. Let's see, V squared versus D spreadsheet. Ah, we have, do we see this point right in here, Alia?
Yeah, I got that on my graph too.
Ah, okay. So that's a outlier. That's why we're getting such a high percentage difference. So whatever students, group of students who did this graph, they didn't pay much attention to this point. If you're performing the experiment in my classroom and I would see something like that, I'd ask you to repeat this data point, not everything else, but only this data point. Okay. And now let's do a little bit of analysis here. Display equation chart, right? 0.2157 for the slope. The slope is 0.2157. I'm getting 18%, just like you got it. But now we are going to do it in a different way, Alia. Look what we are going to do. I'm going to eliminate this outlier and see if I get a better result. Let's see which one is the outlier here. That's D, that's V square, is anywhere between 2 times 10 to minus 1. Okay, it might be 1, 2, 3, 4. There are 4 possible candidates, right? 1, 2, 3. Okay, this guy, yeah, and then also 1 times 10 to the 0. Oh, strange. Let's see why I don't. Oh, yeah, that's because of the D. I gotta look at the D here. I was looking at the wrong place. 1 times this guy is this one right in here. Okay, Alia, is this one right in here, apparently.
Okay.
Yeah, and then how we're gonna do it? We're gonna plot and I'm going to eliminate this data point and see if you get a better. Oh, let's start from scratch. You go. See if we get a better. Okay, I eliminate the outlier, add the trend line, and now I'm getting 0.2485. 0.2485. Let's see what we end up getting. 6% better now, right? So if
Yeah.
we eliminate this, but when if this is for you folks to have an idea what happens when you have outliers like that, okay? But I want you to take into account every data point in your graph, okay, Alia?
Okay, thank you.
Taking account and keep the outlier in there. It's okay. I'm not gonna take out points because of that, okay? And let's go to the next student. Let's see, group 1, all right? Nuhamin, are you there, Nuhamin? Okay, let me put 2 O's here for Nuhamin. It looks like she's away from the computer. I will call now Jazzy Castellano. Did you plot your graph, Jazzy? Hello, Jazzy. Okay, looks like Jazzy is away from the computer. Gabrielle, did you plot your graph, Gabrielle? Gabrielle Contreras. Gabrielle 1, Gabrielle 2. It's not coming out correct. Okay, your graph is not coming out correctly. Let's see. Let's see what's going on there. Help me out understand what's the problem, Gabrielle. I'm gonna get your spreadsheet here, and you plot v square, right? And d. You did that, right? There you go. Let's see. Chart. Okay, see, I get it right. No problem here. Everything lined up well. But every time I try to grab both, it won't let me. Okay, you mean every time you try to grab both of the columns? That's what you mean? Okay, so do you have a Mac or you have a PC? Mac. Okay, so what you're going to do the following. For the Mac, you're going to highlight v square. Okay. Okay. Press the command key. Press and hold the command key. While you press and hold the command key, you highlight the other column. Okay? See if that works now. Okay, good. Okay, so I'll get back to you and then you tell me, let's see, Gabriel Contreras, I'm gonna put here working, all right? On plotting the graph. Now let's go to Liliana. 10 more minutes to go. Are you there, Liliana? Liliana Cortez. Okay, so Liliana is not answering. So let's go for our next. Harry, did you plot your graphs?
Oh, yes, I did.
Okay, or did you get the percentage difference for the acceleration of gravity?
Yeah, so mine was 9.0057.
0.057.
7.
So that's different from Molly, right? Molly got
It,
9.08.
yeah, so I just had a question. I plotted V2 and D, and I put in um the
Let's see,
slope.
let's see. I'm gonna do that. I'm gonna do that here. Let's see what's going on. It's a small difference, but let's see. Okay, b square and d. Now, Molly, here you go. I want Molly to tell me about that too. Let's see. I'm getting 02288, right? 02288. Now let's see. 02288. I'm
For,
getting 89097.
for my slope,
Oh,
for my slope, I got 0.2290.
2290. Your group number 2, right?
Yeah.
Let's see. 0.2290. I'm getting 0.2288.
Hmm.
0.2288. Make sure you highlighted everything. What about you, Molly? Which slope did you get for this graph?
I got 2288.
Okay, 2288. And okay, so and you're getting 9.051 for percentage difference.
Yeah, my data matches yours.
Okay, good. So the interface there with Henry and see what's going on, right? Why he's getting this small difference, and might be something silly, and that you'll be able to find out. investigate, right, the reason for this discrepancy. Larell is here. No. And Danae, did you plot your graph, Danae?
Yes, I plotted the graph.
Okay, what's percentage difference you're getting for the acceleration of gravity?
I'm working on that portion.
Okay, good. So I'm gonna put here working. Now, next here, let's see, Jeremiah. No, Jeremiah already called him, right? Let's call Sean. Sean, you plotted your graph, have been able to find the percentage difference? Let's see, Sean is no longer here. Huh? He left. I'll put that here. Andre, Jason. Jason Straight. Did you plot your graph, Jason?
I believe so. Can I just confirm that it was for the D value and the V squared value?
V square and D. Yeah, your group. And yeah, that's right. What
Right.
slope are you getting?
I got, oh, I might have done it in the reverse order, but I got 0.2397. That's the slope.
97. Okay, and what's the percentage difference you're getting?
The percentage, where did I put that? Where did I put that? How was I supposed to get that again? I'm sorry.
The percent. Yeah, you're supposed to. Here you go. You get your value of the slope, right? Your group number. Let's see. Your group number 5, right?
Yes,
So
group
let me
5.
get this. Let me get the spreadsheet for group number 5. Group number 5. Here you go. Loading. Okay. So I'm gonna plot V square and D chart. Whoa. Slope trend line display equation chart 0.2397. Is that what you got? Let's see if what you got. 2397. Yeah, okay, good. So we are getting the same value, okay? So it doesn't look like you didn't see it. Now what you are supposed to do? You're supposed to get the numeric to write down the numerical value here for the slope, right? 0.2397. Here, you should get 5%.
Oh, I see. Okay, I got this.
Okay.
I got the same slope as you. Thank you very
Okay,
much.
good. Welcome. Okay, we're running out of time. 3 more minutes. And there are other things that you should do, right? But the most important are the V square, log the slope in the last table, check the percentage difference, and then you go ahead and finish the rest of this lab at home, working as a group, right? Fill up the units in the table, display the proper number of significant figures, find the CL. Okay, find the CL, fill up all tables, okay? Okay, so any questions? Two more minutes to go. If you don't have any questions, so we can stop now. And I see you on Monday and have a nice weekend. Okay?
Thank you.
Welcome.
Bye, Professor.
Bye-bye.
Hi, Professor. This is
Yeah.
Henry. So I just I'm still curious of why mine and Molly's were a little bit different
Okay.
on the slope.
Uh-huh.
Is it, would it matter if I change the format and then the number to like scientific, or would I have to have the number to automatic?
No,
Like the
it doesn't make any difference. Okay.
difference, right?
Yeah, it doesn't make any difference if you change the format. Maybe, I suspect, okay? That's my suspicion because I do not know what. Maybe you mistyped something in the cell, okay? Maybe that
Okay.
you interfere with the cell, right? By typing
Hmm.
a number what you're not supposed to type.
Okay.
That's a possibility, okay?
Okay.
Do you want to share your screen with me? Share your.
Oh yeah.
Let me see if you can figure out what's going on. And let's see. Blah, blah, blah. Oh, you can upload your spreadsheet. Why don't you upload your spreadsheet? Upload your spreadsheet to the group folder, and then it's
Oh,
gonna be easier for me to,
you want me uploaded?
yeah, upload it. Upload to
Okay.
the group folder, and then it's gonna be easier for me to see
Got
what's.
it. Okay. Oh,
Let me know whenever you have uploaded.
okay. Sorry, I deleted the graph because I was trying to like keep on putting a new one in, but I just put it in and then I'll just um do I just import it or
You just click, drag and drop. Click, drag and drop.
so I should hmm, make a copy. Okay, I made a copy in mine. Just it should be the first one.
Copy this one here. Yeah,
Uh,
this one, right?
yeah, on the way top. Yep, yep.
Okay, let me download it. Okay, enable editing. Okay, that looks like a little bit suspicious, but I guess that's okay. Let's see this one. 2288, right? And we're getting what? Yeah, 2288. Okay,
Oh,
so it's nothing. Huh? See the slope here? 2288, the same slope that me and Molly got. Now you gotta log. Oh, see, you log 2290. That's why the percentage difference is different. Okay.
right. I don't know why I got 2290 in the beginning.
Yeah,
That's weird.
2288. And now you're getting, I know, the same thing that Molly got, right?
But still on my my graph that I'm looking at,
Uh-huh.
uh my slope still says 229, 0.229, but on
That,
yours,
oh,
when you open it,
oh yeah, there's a reason. There's a reason. Okay, now we found out the reason. The reason was that because you are using only three decimal places. Okay, that's
oh,
why he's rounding up to 229. That's
so
why.
how can I change that on my
Uh,
computer?
okay, so here you go. Click the box here, right?
Okay,
Click the box, right click, format trend line label.
how come I don't
Format
see that?
trend line label, and then you choose the category number, right?
Uh-huh.
And you choose the number of
Three.
decimal places. If I want to put like 6, for instance, right? It's gonna show 6 there, right? 1, 2, 3, 4, 5, 6, right? If you
Yeah.
wanna well, display 4, so your number is the same as Molly's.
Do you know, because I'm doing that on my Mac, but
Uh-huh.
it's not showing able to format. Maybe I need to click separately and I can't right click. So
The Mac in general allows you to do that in those boxes right in here. You see,
yeah.
you know, you gotta access. Let's see. And lime. It doesn't let you click this box here.
It does.
It
But
does.
if I right click it,
What about right click?
yeah, right clicks it, but I don't see the like the format or that. I just see like chart area, chart style, chart axis and titles, series, legend, axis, grid lines, and data range. That's the only options that I'm getting.
I see.
Which is weird.
I do not know. Okay.
I'll try to figure it out, but that's probably why.
Try to figure out. Try to figure out and let me know so I can next time I shouldn't have the same problem. I can help.
Okay.
Out.
All right. Thank you, doctor.
Welcome.
Bye. Have a good weekend.
Tá ficando quente, né? Vamos sim. Vamos ver. Desconto. Ai. Oi. Gente, não é cara. Eu não tenho ciência, eu não tenho. Deixa pro marido.
Hi, Professor.
Yes.
Hi. I wanted to ask you something. It's just because I'm using a different computer. How do you, on the Windows, do you know how to, do the, sorry, how to add the RX value? Like,
Rx.
yeah, for the slope.
Let's, let's see. Which group are you with?
I'm in group 5.
5. Okay, let me get here your spreadsheet. Okay, so here's the spreadsheet, right?
Mm-hmm.
What do you want to do? I didn't quite understand.
Oh, I wanna get the formula, the equation. Do you know how to do that on the
Which equation for what? The equation for what?
for the chart? Like I already got
Okay,
the
okay, okay, okay. This equation here, the regression equation, right?
yes.
Okay, okay. So let's do from scratch. Okay, so you highlight v square, right?
Well,
You
v
highlight.
square is first.
It doesn't matter. Doesn't matter.
Oh,
Can be the first, can be second, and then you highlight d.
mm-hmm.
Can you do that?
Yeah, I
Okay.
already did that.
Okay. Insert, chart, scatter, right? Do you get a graph like that?
Yeah.
Okay, good. Click one of the points. Everything is highlighted.
Mm-hmm.
Right click at one of the points and you add trend line.
Okay. Yeah, I have that
Okay.
also.
Now, do you see this pane showing up on the right side of your screen?
I see.
Something like that should show up in your computer, in your screen.
I have. Oh, wait, I think I got it. Okay, I
Okay.
think I. Oh,
Display
let's
equation
see.
chart, check display equation chart, check R square value on chart. That's what you have to do to display those values here.
Okay. It's okay, yeah, I think I got it now.
You got
Yeah,
now? Okay.
got it. Okay. Right. And then so in total we have to have 2 charts? I mean, sorry,
No, just one chart. Just one.
or just one chart?
Yeah. V square versus
Okay.
E.
And then we have to find the rest of the information for the lab, right?
Yeah, that's right. Then you log, you log this slope at
Mhm.
the last table, right?
Yeah.
You get the delta percentage difference. You fill up all the units
Mm-hmm.
like it is here, right?
Yeah.
Unit, unit, and units, right?
Mm-hmm.
And then let me get Danny in, and then you display all the numbers and results with the proper number of significant figures. Okay. What is in red, you do not have to worry about significant figures. Okay, so only those that you have to. And what else? After you do all of that, then you fill up this table here of CL, right? And
Yeah.
the equation that you got in the graph, R squared, and determine the other CL, the two CLs, the lower bound and the upper bound.
Okay. Okay. All right. Thank you, Professor.
Welcome.
Bye.
Bye-bye. Do you need any help, Danae?
Yes. I feel like she probably just asked exactly what I needed help with. Okay, so I got the graph, or yeah. Um,
Tell me what's
and
your group number first. What's your group number?
3.
3?
Yes.
Okay, so let me get your spreadsheet. Let's see, not this one. copies, group 3, right in here. Okay, so here you go. V square, you plot the graph, right?
Yes.
Okay. So here you go. Plot the graph. And you display the R square and the trend line, right? Did you do that?
Add trend line, yes.
Okay. Now you get this is low.
Yes.
0.603.
Okay.
Go to the last table.
I
Unlock.
input that.
0.2603.
Mm-hmm.
Right?
Yes.
That's gonna be the acceleration of the cart. That's gonna
Okay.
be that's gonna be your experimental value for G, and that's gonna be your percentage difference from whatever is here at the top.
Okay.
Okay.
And then as far as for like the rest of the red values, it's like for R squared, am I getting that from the, so is it 0.999?
Yeah, you get 0.99. Let's see what you got here. Yeah, 0.9999. Yeah, that's right, 4 decimal places.
And then for V squared, where am I getting that from?
Okay, the V squared is just the regression equation. See, I wrote down the regression equation here.
Also, just put the whole equation.
Yeah, the whole equation. You copy it and you paste there.
Oh, okay. And then for N will be like all the numbers. I mean, what is it? 1, 2, 3,
Yeah.
10, right?
Yeah.
So we did 10 tests. Okay.
Uh-huh.
Okay. Is there a way? Is this your office hours right now?
No, my office hours on Monday.
Only on Monday. Okay.
Yeah.
Is it so for the next class? Could I stay afterwards and can we work on review the first exam, please?
Uh-huh. Yeah, we can do that on Monday.
Okay. I just couldn't do it this Monday. I had an appointment I had to get to.
Oh, okay. That's why you couldn't do it.
That's why I couldn't do it. Yeah.
Okay.
Okay. Thank you, Professor.
Okay, thank you. Bye-bye.
Bye.
Hã? Ah, aham, deixa eu sair.